Okay, let's get started. So maybe we'll get started. A number of things. A few people have gotten into wait in the class. It's still a long wait list, so we're waiting for people to start dropping or adding classes. And again, that's out of our whole point of this waitlist system is to make sure instructors have no control over who gets into the classes. For better or worse, that's the system we've got. There have been a couple of additions to the course website, which I want to talk about. So one is the course wiki. And if we go to the course wiki, this is what I use for students to ask questions outside of class. And the reason for that is if you email me a question and I answer to you, and then someone else might have the same question, and they email it to me, and then I email it back, and then I start getting 5 or 10 questions, the same, similar questions, and then 5 or 10 people get it, and it consumes lots of my time and doesn't get everyone. So if you post it on the wiki, right, then what happens is everyone can see the question, everybody can see the answer, and also there will be times when students will ask questions and some other student may know the answer, and then they don't have to wait for me to go to the wiki and start trying to answer. I'm not going to sit there every hour checking the wiki to see if any questions. I might do it once or twice a day. And I presume these days everyone knows what a wiki is. I mean, Wikipedia has made that pretty famous. And so it's basically a page everyone can edit, a site where everyone can edit. And when you go there, there's an edit button. And now what's going to happen, the first time you go there, it's going to ask for a username and password. All right? And there is a reason why I don't publish the username and password on the network. I can't use their special board, so I have to do the old-fashioned way. And let's see, I guess we could try it here. And so you can do, there's 2 words, and you can use them either interchangeably. One is the password, one is the username. So it's SDSU, all lowercase, or the other one is CS696. So those 2 should be relatively easy for people to remember. Right, so it's CS696, either all lowercase or all uppercase, and then San Diego State, all lowercase, SDSU, and one can be the password and one can be the username. It doesn't make a difference. Once you go there, like I said, there's this edit button, and then we can start adding the page, and then there's a save button, right? And the page is now changed, right? Now, once you have a system like this where everyone can edit, there will be times when 2 people try and edit at the same time. And what happens is there'll be occasionally times when person A saves and person B saves almost immediately afterwards, and then A's changes go away, right? It's not supposed to happen. You should get oh, sorry, but the page you edited was already edited with someone else, so you need to do it. But sometimes it happens soon enough that happens. And in that case, there's a history that shows all the edits that we made in the page, and then we can say, well, what did it look like in version 1? And there it is, right? So you don't have to worry about if you make a mistake. You can always go back to history and see what it was like before, and then you can correct the error, right? And there is this special page called the Wiki Sandbox, and the whole point of that page is just so you can practice editing so you don't freak out about, oh, how do I do this? I might break something. Questions? Okay, so we can go back. The other thing we added was the course portal. This is where you'll turn in your assignments. And when you go there, you'll need to create, if it's your first time, you need to create a password. If you log in, use your red ID, and then create a password for yourself. Now again, you create a password, but there's a list of red IDs which are approved. So as people add the course later, I'm not going to check every day whether someone who was added. I probably look at next Wednesday or Thursday morning and see if I need to update someone's red ID. But until I add your red ID to that list, you won't be able to sign up. Right, I did it this morning, and so everyone who's registered in the course this morning should have the ability to actually go and create an account here, and then they can upload for assignment 1. Okay. And now I want to jump ahead to document 3. Yeah, I did. Usually the first week or 2 of the semester, I get to spend about 2 to 4 hours a day answering email. And so I haven't gotten to it. So I want to talk about Jupyter Notebooks. So Jupyter Notebooks are fairly popular in data science and allows us to mix text and code in a way in which we can execute them. And so let me take a look at so I've created a number of notebooks. This one will take a little while to start up. And so this is a notebook I created last year about Amdahl's law. And so we can create text. And so it explains things about Amdahl's law, make it a little bigger. And then we can scroll down. And then there's going to be, another cell which has text, code in it. And we can actually in here execute that code and see the results, right? And in this case, the result is a nice graph. And if I select the cell, I can now execute it, and it's going to take a while because right, let's see, do I have a manipulate there? Yes, it's going to take a while. But allows us to intermix code, text, in this case even graphics, right? And now I should have gotten the output. Still not working right. One more time. And this is important when you're trying to explain your results to other people, right? What we're used to doing is we're used to writing the applications and then here is the source code, right? Or here is the application. Or, oh, I wrote a back end to the server. Now here's how, I install it, make it run, and we check, make sure it's working. But in data science, we're doing exploring of data, right? And it's nice to be able to say, look, here, I did this, here's the code, here's the output, here's why it's important, right? You may be doing lots of experiments, and so how do you keep track of them? You probably do this when you're learning a new language, a new system, you try this, you try that, you do a bunch of different things, right? And where do you store those experiments? Well, one goes in that file, and it goes in that file, and this file, and then you got 15 files, and where did I do that thing? And you look for the files. So it's a very, here we go. So, yeah, come on, it's finally working. So this is actually interactive. So, everyone know Amdahl's law? Yeah, we'll come back to it in a little bit, but we'll just let me hide as much as I can. And let's get a little bigger. So it's both interactive, so I can start changing parameters, and we'll see the graph start changing. Right, so I got text, I got code, I can execute the code, I can start doing graphics, I can interchange things, start changing parameters. So we'll start using this as a way of turning in your assignments, right? So in assignment 1, I expect you to create a Jupyter notebook that runs Scala. And, then for problem 1, you can say, here's problem 1, here's my code. Here are some code that shows you that works correctly. And then you upload it. And then I take this whole thing and I download it and I put it in Jupyter notebooks and I run it. Oh, it works, right? And there are a couple of questions where I ask you, well, do this to tell me the result and explain the result, right? Or show me what happened, right? And again, so in the notebook, you can say, look, here's my code, here's the output, and here's what I think is going on, or what the error is, or what has changed, right? So it's something that you may not be used to, but it's very common in data science. So far, so good. Questions? So the question is, if you have lots of data, if you got a data set, whether it's small or large, is a way of embedding in the data set notebook. The answer is yes. You may not, if it's 100 megabytes or gigabytes, then we need to start worrying about how to transfer it. We can also take these things and put them on a server, and then people can access the page from the server. Then it becomes slightly easier to deal with larger data sets because then it's all in one machine rather than everyone have to download it. But there is a way of doing that. Let's see. Okay, now I need to give me a toolbar. Now if I go back to home, so there is this upload button, which allows us to upload things. There's also this new, and I've installed with a bunch of different kernels. For us, what's important, we want to do the Scala kernel, and so now I can create a new notebook that runs Scala. And once I've done that, now I can, type a Scala expression. Here's, well, we can. So, right. And I can now execute it. It has to take a while and so it executes that Scala piece of code. I can also, when I do that, I create another cell. I can change that cell from code to Markdown. And Markdown is a common way of indicating HTML text without having to do all those angle brackets. I can just type and I can start typing text, and I can start doing various Markdown things. Right. So far, so good. So I expect you, I'm gonna do, problem one. Here's my code. Here's the output. Here's some might be. Is that how you want to write the question? Yeah, I mean, basically say, look, here's my assignment, right? Instead of handing a piece of paper, we're putting it down in a notebook where someone can come and say, oh, here's what's going on, right? And the goal is twofold. One is it gives me a uniform environment, which I can then look at your code and execute it. Well, this person uses Emacs, this person uses VI, this person uses Eclipse, this person uses IntelliJ, and then trying to figure out how to execute all this code. Right? So it's like, okay, it's in this format. You upload it in this format. I download it. I just then run my Jupyter notebook, and I can look at each one. I can run your code, make sure it works, right? And the second goal is, this is very, very common in data science, right? I frequently quite often come across people talking about they do all the work in a Jupyter notebook. Personally, I find Jupyter notebooks not a very good development environment. You don't have a debugger, right? So if you start writing off the code and something goes wrong, it's like, you would like a debugger to show, look, I can step through and see what's going on. That doesn't happen. So typically what I do is I use another environment to try my code out, get it working, and then I will put into Jupyter Notebook, right, and add the text. But there are people who do data science, they do all their development in a notebook like this. Questions? And so if you go to Jupyter.org documentation, there is a list of kernel, section for kernels, and there are 3 common high-level kernels that they highlight: Python, R, and Julia. The Jupyter one, you have to go to community maintained, and when you do that, there's actually a couple kernels that do Scala. Use the Jupyter-Scala one. If you look at the 2 Scala ones, the first iScala, the project has not changed in 3 years, which is a bad sign. And you go to this one, I think it's been changed a few weeks ago or a month ago, and they're both on GitHub. And so look at the stars and number of downloads, and clearly this is the one we want, right? Okay, any questions? And when you go there, they tell you how to install it. And has everyone downloaded Scala? So when you say you've installed Scala, have you installed the Jupyter Scala kernel? If you have installed the Jupyter Scala kernel correctly, then when you go to the notebook and create a new notebook in the drop-down menu, you should see Scala. Yes. So how are people running Scala code? Has anyone tried compiling Scala programs? What's that? Anyone else? Yeah, so Scala, there are a number of ways you can do it. One is command line, right? A lot of languages sort of talk about, we have a REPL where you can type in a line of command and execute it. That's sort of nice for trying things out. And Scala definitely has that. There are a couple of commands you might want to know about. One is help, which tells you what you can do. Another one is load, so you can load a file, so you can edit a file and load it, and then try it out. That makes it a bit more useful. And they also have tab completion, so you can actually hit tab, and then it will tell you, what. There are a number of IDEs that support Scala. One is Eclipse. I stopped using Eclipse a number of years ago. so I don't deal with it. IntelliJ does support Scala, and you need to download IntelliJ. Want to do that, and there's a plugin that you have to install, and then start a project, and they have a page that talks about that. To actually, when you download IntelliJ and install the plugin, you can then select the version of Scala you want, and I showed the steps here, and I'll let you look at it when you have to use it. Right, and again, how to add a particular version of Scala to your project. And so you should definitely, if you want to use IntelliJ, you should definitely download it and start working on it. So far, so good. What? Yes, I did tell you last time that you'll be installing things, right? And you're graduate students in computer science, so when you get done and people hire you, they're going to expect you to be able to do this sort of stuff, right? So what I'm going to do now is I'm going to go back and talk about sort of the introduction to big data, and I hope to stop lecturing earlier so we can talk about some special things in this room. So let's I want to go back to document number 2. Yeah, what is big data? There's, it takes big data sets, right? To give you an idea of the scale, right? Hulu, right? Everyone knows about Hulu, this crazy site that lets you watch TV. It's slowly evolving. They claim they get 20 gigabytes of data every second, right? Because all these new shows that they're reporting, that's 20 gigabytes per second. And that's not like, oh, it happens once in a while. It's like, no, it's happening all the time, continuously for hours and hours and days, right? Let's see, 20 gigabytes per second. So every minute that's 1,200 gigs per minute, right? Per minute. There was this LESS project to analyze, the Berkeley project analyzes, all these images from astronomy to find new stars, etc. They processed 55 terabytes of data, right, in 15 minutes. Intel announced what they call, the nickname is called the ruler, because it looks like a ruler. What it is, it's a solid state drive, 32 terabytes. It's meant to go into a rack, which means you need an enclosure to put it in. The closure holds a number of those things, so you can put 1 petabyte in one of these things in a rack. And of course, it's a 1U mount, so you can put a bunch of them in a single rack. Right? And my guess is there'll be some companies that will be filling racks of these, right? How much it cost? I don't think any one of us in this room are going to be buying one of these things anytime soon. In the press release, they did not give the price, right? So, you could fill an entire rack of these up and you get 42 petabytes of storage, right? Amazon has what they call their Snowball. It's a device that holds up to 80 terabytes. And what you do is you say, I have this data I want to upload to AWS. Send me one of these things. You plug it into your network and you download all the data and you put it back on a plane and ship it back to AWS, and they will then put it in their system. Why? Because it's faster than sending 80 terabytes over the network. They introduced this a couple of years ago, and then they introduced their Snowmobile. It's basically a semi-truck that pulls up to your site, and then you pull out of it this fiber optic cable, and you plug it into your network, and it can hold up to 100 petabytes of data. And you fill the truck up with all this data, and then the guy drives off back to Amazon Center, and they do the reverse, right? Again, to send that amount of data over the network is going to take you decades, right? Decades and decades. They didn't say. When I saw the keynote speech a year ago when they did this, and they didn't announce how many trucks they had. And, just a reminder, a petabyte is 1,000 terabytes, which is 1,000 gigabytes. And Amazon claims they have customers that have exabytes of data, 1,000 petabytes. Right? This is really big data, right? People have lots and lots of data. The scale of computing these days is crazy, right? I read this summer that these companies that do mining for Bitcoins and other, right, digital currency, there are times when they'll rent a 747 and fill it up with GPUs and fly to the site. Why? Well, because they don't want to wait the 5 days it takes to get shipped there. Because when you have that many GPUs, those days, it's just, you could earn a lot of Bitcoins, right? So when people talk about big data, some people like to talk about the 5 V's, and some want to talk about the 4 V's. It's one of these things where they choose the words trendy. One is the volume. You just have large data sets, right? Terabytes, exabytes, petabytes. Another is velocity. You have this data streaming in, like Hulu's got, this data streaming in. Variety, you have different types of data coming in, right? It's different formats, some structured, some unstructured. And the data comes in intermittently, different types. Veracity, some may be highly accurate, some may be of dubious value. So dealing with this type of data, right? Many people, when you read about big data, they think about this large data set. They don't think about these other issues. Now, as your data set gets bigger, there's two ways of trying to deal with it. One is what they call scaling up or scaling vertically. Just get a faster, bigger machine, right? Add more memory. like I said, AWS now has instances that have 2 terabytes of RAM. If you've got a choice, scaling up is always easier, much less work than scaling horizontally, right? At some point, when things get too big, you have to use multiple machines, and then there's all kinds of problems occur, right? So you've got a choice, scale up. And then throughout the semester, we'll talk about various problems that occur when you try and scale out. That's what we're going to look at. So Amdahl's law, this is one of the things that, sort of a simplistic model saying, look, right, we have some sort of program we're going to run, and not all operations will be done in parallel, right? When we use multiple machines. Some parts are sequential, right? First you have to do A, then you can do B. And if A has to be done before B, it doesn't matter whether you're using 1 machine or 100 machines, right? You still have to wait for A to finish before you can do B, right? So using multiple machines doesn't help. So basically, what Amdahl's law says, look, what you have, there's going to be a certain percentage of program which can only be run sequentially, right? First I have to do A, and I do B, and then I can do all this other stuff in parallel, right? And then we take all the remaining stuff that can be done in parallel and ask how long will it take to do that using N machines or N processors. But T1 being sequential to run it, T of N to be, right? And the speed up is just going to be, right, sequential time versus parallel time. And Amdahl's law says, look, if P is a percent of the program that be parallelized, then your speed up is going to be given by this. So if P is 1, then we get, well, 1 minus 1, which is 0, and then plus 1 over n, which is divided into 1, so we get n, right? So if P is 1, then the best speed up we can get is going to be a factor of n using n different processors. Now, if P is less than 1, right, then this is going to be less than n. Right? So when P is equal to 1, we get this. When P is 0, right, then the best we can do is 1, right? Given that formula, given P, how many processes does it make sense to use? Anyone have a guess? Here's our formula, right? P is 0.5. Everyone's going, he wants me to actually do some computation in my head. Are you crazy? And so it's like 1 minus 0.5, that's 0.5 plus 0.5. Yeah, when does it make sense? Does it make sense to use 100 machines? Does it make sense to use 50 machines, right? right? We could do that, but then everyone's like, now what do I do, right? This is slightly irritating to have. So we said P equals to what? 0.5. Okay, let's take this P. 0.5, right? And there is the curve, right, of the speed up. Well, let's change n, max n to be something smaller, say 10. And look what happens, right? All of a sudden now, here's this, so I get a little speed up, right, but not much. Does it make sense to use 10 processors? No. Does it make sense to use 5 processors? Not really, right? So what if P, well, what if P is, say 0.7323, right? We're starting to get a better speed up, right? And now it might make sense to use 5 processors, right? Say 0.9, right? What happened to 0.9? Now all of a sudden, oh, that speed up is growing pretty good, and so it probably makes sense to use 10 processors. We might want to look at, make the chart a little bigger, down. Right, we could start seeing what's going on, right? So we had a fairly simple equation, right? And when I ask the question, everyone's going like, well, I think we just do this, and like, But as soon as we can visualize it some way, right, the answer becomes much clearer, right? So we're doing data science, right? And you've got a pile of numbers. It's hard to see patterns. It's hard to see what's going on, even with that simple equation. So visualization becomes an important tool to help us understand what's going on. Okay? Now the problem with Amdahl's law is it's very simplistic, right? One of the problems we have is that when you've got multiple machines, the machines have to communicate, right? And communication is slow, and if machine A needs result from machine B, it may get there to the point that it needs result before machine B is ready to give it, right? So it has to wait. So it can become inefficient. So people have modified Amdahl's law to take into account communication costs, right? So again, this notebook, right, derives the equation where C is the percent of communication costs we have, right? And then we can do the same thing with, right, in this case, P is some value, and then C, communication cost, right? And again, the speed up we get becomes this curve. And what becomes interesting is what happens when the communication cost increases. And what happens to the speed up curve? It goes up for a while and then it decreases, right? Which means adding more machines actually slows the process down. It takes longer, right? Communication costs are too expensive. And the more machines you have, the more communication you've got, right? And it's very slow. And as you add more and more machines, you spend a larger percentage of time just sending messages back and forth. So it's not just that oh, I've got a problem to solve and it's too slow on 2 machines, so I can add 10 machines or 20 machines or 50 machines. There could come a point where adding more machines is going to slow things down. All right? So again, there's 2 messages here. One is, right, visualization is important to help us understand what's going on. In this case, adding more machines may not be what you want to do. Okay, so far so good. Right, and we can start asking these questions. If you want to speed up at 5 or greater using 10 processors, what p-value do we have to have, right? And again, answering this question by the equation, it can be done, but again, you can be like, oh, how do I do that? What do we do? Visualization can help us, right? Just graphing that allows us to answer this question is a lot easier, right? Just seeing that equation is going to take us a while to figure out what the answer should be by hand. Now they start looking at Spark. What we'll be doing is with Spark, we're going to be taking data and we're trying to analyze it, do some of the data, and spread it across multiple machines. And the whole idea of Spark and Hadoop is that we're not using specialized machines, right? We can buy special processors and special machines which are designed to run in parallel. You go to the supercomputer center, they have a bunch of them. But the whole idea of Hadoop and Spark is you just buy a bunch of commodity machines, you put them on a local area network, and they work together, right? Now we see if you have these machines, they've got communication costs, and the question is, when will the communication cost be too high, right? And you want to use 10 machines and not 100 machines. How many machines do you want to use, right? How do we distribute the data, right? How do we find the data once we distribute it, right? How do you know where it is, right? What happens when the machine fails, right? We got 10 machines solving this problem, one goes down, now what, right? Right? Hopefully not, right? Hopefully we don't have to start over. And if we start looking at Spark has solved these problems. We have to understand how they solve them, right? If one machine goes down, we need the data that it contains and we need the code that it contains, right? So what happens? How does it deal with it? What does it mean for a machine to fail, right? How do we know when a machine has failed? How do you write code to say that machine is now dead or no longer responding? If it doesn't respond in half a second, does it mean it's down? A second? 2 seconds? When do we decide that machine is down? And what happens if it's slow? For some reason, it's churning away and it's too busy to respond. And you decide, okay, it's down now, it's gone. So now Hadoop or Spark spins up another machine to take its place. And then when that new machine comes on, starts helping out the old machine now, I'm here. What happens, right? How do we deal with that? How do we distribute the computation, right? To make sure that we don't want one machine to get all the work and the other machine is waiting. Oh, I'm not busy. I guess I can go play, some game. Right? How does computation get shared between these machines? I have 10 machines solving the same problem. How do we get the results from one place to the other? How do we deal with that? How do you combine results, right? I've got 10 machines. They've done their part. How do I combine those answers together and then get it to one machine where I can look at the result, right? Even on a single machine, right, there's a lot of tweaking you can do to optimize how well that machine performs, right? And so there's going to be more opportunity to do performance tuning when you have a cluster of machines, right? So as we start looking at Spark, keep these questions in mind because we need to know the answers, right? Because as computer science students, if you get hired to deal with Spark, they expect you to know what these are, and they expect you then to be able to act appropriately, right? No, we don't want to use 50 machines on this problem. Your problem is taking too long. Well, when you guys got the master's degree in computer science, how do we tune the machines to make them work faster and better? Not all problems are good problems to solve using Hadoop and Spark, right? So I want to look at sort of two extreme types of problems, right? One is, they call them now pleasingly parallel. And so let's say I've got a bunch of numbers, get a small set, but it could be, 10 gigabytes, or 100 gigabytes or terabytes, right? And there's a contest that people run, and I think they give you 100 gigabytes of data, which you have to sort, right? What's the fastest you can sort that data in using a cluster, right? If I want to compute the sum and I want to use multiple machines, processors, well, we can just split the data up, right? And send, in this case, 2 machines, half the data there, half the data here. I can then compute the sums on those 2 machines independent of each other, right? And then I can take those 2 sums and send them to the same machine and just add it up, right? Done, right? It's called pleasingly parallel because the task we want to do can be broken down into n independent tasks that can be solved completely independently. And then when we're done, we can then just combine the results, right? So the amount of communication we need is basically 0. You send it out, you do the computation, you get the answer back, right? So the communication costs are very minimal, right? These types of problems are the problems that Hadoop and Spark are designed for. Look at a different problem. You want to simulate weather, right? We do weather forecasting, and so what you do is you set the simulation up. You start, okay, here's the current situation. We want to simulate it to see what's going to happen tomorrow, the next day, etc. So this is a particular model that people run. What they do is they divide the area you're interested in studying into 4-kilometer cells. And you can imagine if you can divide the United States into 4-kilometer cells, there are a lot of cells, right? And then what you do is they also then, since it's weather, you're worried about the atmosphere, right? And different parts of the atmosphere behave differently. So they then have 35 vertical layers, right, of atmosphere. And then what they do is they run this simulation in time steps of 24 seconds. So what you have to do is each cell, you have to worry about, okay, there's solar input, right? And that depends also upon the condition of the layers, because it might be cloudy, it might be foggy, right? And so then you compute how much solar energy is in each layer, and then what happens when it hits the ground. And depending on the type of ground you've got, different things happen, right? If it's all concrete, and that heats up fast, and it really puts a lot of heat back into the air, right? If it's forest, the leaves really absorb a lot of that energy. And once you've done that, right, that affects each layer. It affects how the wind is going, right? And so you compute the solar energy in each layer, you compute its effects, and then what happens is each layer interacts with the other layer, right? So if one layer gets hot, then that heat is going to be propagated particularly up and a little bit down, right? The same thing with the ground level, it's going to propagate, but also individual cells are going to interact with the cells next to it, right? If several cells have lots of energy, it's going to heat up the atmosphere, and it's going to change the wind velocity in that location, and that's going to affect the corresponding cells. So the simulation basically goes, you go through in each cell, and you do these terrible computations, right, of adding the solar energy and the effect it has in that cell. And then when you're done that, you have to then look at the interaction between corresponding cells and layers, right? You go, this cell and this cell interact together, and so you interchange the data, right? And you do it with layers too, right? And so there's lots of computation, right, to deal with this. And say, oh, this is natural for using multiple machines. So the problem becomes, okay, so I do this computation for each cell, each layer, but then I have to see how they interact, right? Which means if I want to see what the interaction of this cell, I have to look at the interaction between these two cells and these two cells, right? And if I divide this in multiple machines, multiple processors, right, I can then, right, do some grids here and some grids there. But the problem is now, how do I deal with the boundary here, right? Because this cell is going to affect what happens in that, right? In a different processor, different machines, that means this interaction requires communication between the two processors. So each time step, you're going to compute the effect of the solar radiation on each cell, and then affect those changes, how they affect boundary cells, right? And each time you do that, no matter how you slice these cells, there's going to be cells on one processor and cells on another processor, and there's going to be a boundary, and there you then have to send that data back and forth. Cell A needs to talk to cell B, and they're different processors, and so there's communication costs. And that happens every cycle, right? And if you want to simulate, say, a week's worth of weather, and your cycle time is 24 seconds, that means a lot of time steps, millions of time steps, right? And each time step is going to require communication between the two processors. A lot of communication costs, not a good thing to use Spark or DuPont. It's not going to work, right? The people who do these complex models don't bother looking at Hadoop or Spark. They look at it and they laugh at it. And, no, come on, you guys are silly, right? This won't work. We have a computational science program, and a lot of what they do is they build models and simulate those models. For those people, Hadoop and Spark are like, what? Because they have a lot of communication costs between processors, right? And once you do that, Hadoop and Spark are not designed to solve those types of problems. So far, so good. Yeah, so the communication costs. So Hadoop and Spark, the goal is we don't want to do a lot of work, right? The people who build those models and program them are like, okay, I'm going to use 10 machines, 10 processors, and we're going to name them all, and we're going to then, this machine is going to talk to that machine. We want to automate this as much as possible. We don't want to know how many machines we're going to use, because today it might be 2 machines, tomorrow maybe 20 machines. We really don't want, we want our code to be completely independent of the number of nodes we use. We want our code completely independent of knowing, we don't want node A having to talk to node B, because then they have to know there's a node A, and they have to know where node B is, and then exists one, right? Now, I said, summing things up is an obvious, simple, pleasing parallel, perfect for Hadoop and Spark, even though it's too simplistic. So here I have, sort of code to do this, right? I mean, you read the data into an array, and then you sum equals 0, and then you iterate through the array, and compute the sum, and we're done. We know the sum, right? How are we going to parallelize that? We're going to do it in chunks, right? But there are no chunks here, right? There are no chunks. So either we rewrite the code to take into account, we're going to break the data into small pieces, which means we have to rewrite the code, which is sort of bad news, right? Or we can have the compiler to rewrite it for us, right? The problem with doing that is today we may want to use 1 machine, tomorrow 2 machines, and next week 10 machines. And so we don't want the compiler to know how many machines we're going to use, right? And so having the compiler do it becomes a very, very hard problem. And in particular, if the compiler is going to do it, what can go in that loop? Anything, right? Maybe, the programmer says, I'm going to make things faster by doing this, right? Which means once you do that, now how is the compiler going to figure out where the data is, right? It's not going to work, right? It's not going to work. So here is a Scala program which we can use to compute the sum of that array. It uses a function called reduce. How does reduce work? Reduce works by saying, what I'm going to do is the very first, when I call reduce, the first thing I do is I'm going to take the first 2 elements of the array and pass it in to this anonymous function. And so it's going to sum up first element, second element. Then what reduce does, it takes that result and passes it to reduce that anonymous function with a third element of the array, right? And it keeps on doing that until we've gone through all the elements of the array, right? there's a fundamental difference between that solution and this solution. One is the programmer does not have access, is not indexing into the array, right? We're not saying, give me the array location 10. We're saying, here's a function and it does what I want, and the reduce function is going to go through and pass it one by one, all the elements. All right? Question is, does it reduce? When you're done calling reduce, then if you created garbage, there'll be garbage collected. Well, what reduce does is basically this behind your back, right? And so you've got a local variable k, and the local variable keep track of the sum. And when reduce is done, those go away. The same way it goes away when you finish this code block. Which pointers are we talking about? Well, if data is an array, reduce doesn't get rid of that array. And we'll come across reduce later. Since a programmer does not directly index into the array and reduces a function call in a library, we can write that function to automatically parallelize things, right? And so it becomes easier for us to write a system where reduce is used to run code on multiple machines. And so what happens is that the Hadoop people and the Spark people have used functional programming to write libraries to make it easier to distribute computation and recollect the results. So it's a library call, it's a function call, and we can rewrite that library to either work on a single machine or multiple machines. Let's see, I'll keep on going. For this class, I found it's been not really talked much about Hadoop, but mainly Spark. This is a Google Trends chart, which shows that the Spark is gaining momentum and Hadoop is losing momentum. And there's a couple of good reasons for it. And to talk about that, I want to step back for a moment and talk about something, latency numbers, right? Everyone knows L1, L2, and L3 caches are. If you don't, you probably are too embarrassed to say, right? You don't know what L1, so when you get a processor, right? Main memory at a certain speed, but we can write, there is memory which is much, much faster, but it's more expensive. And so what we do is in each chip, right, we'll have a cache on the chip, which is memory, which is much faster than main memory. And so L1 is going to be the fastest possible memory we can buy. L2 is faster than main memory, but not as fast. So right? And so we have these levels of caches. Each level, the highest level tends to be a smaller one because it's very expensive. And L2 is less expensive, so it can be bigger, right? but it's slower. So L1 cache in half a nanosecond, we can fetch data out of it. L2 cache, 7 nanoseconds, right? A main memory reference, 100 nanoseconds, right? Ooh, yes. Yeah, so this data set came, is several years old, was probably 5 or 10 years old by now. But we're still getting those relative speeds, right? Um, yeah, that I really can't answer you. Now, main memory is 100 nanoseconds, right? Reading from the SSD is 150,000 nanoseconds, right? Um, going to a disk is like really, really slow, right? Now people try to make these numbers more intelligible, and so they multiply a billion and say compare it to things we normally do. So in this case, the L1 cache is like half a second. L2 cache is like 7 seconds. Main memory is 100 seconds. Give you an idea of how much longer it is. And the fun part comes here, where reading from an SSD, 1.7 days, relatively speaking. Reading 1 megabyte from memory is like almost 3 days. Reading a megabyte from SSD is like 11, almost 12 days, a factor of 4, right? Using a hard drive, doing the seek, and then reading it takes a year, right? To give you a feel for how much longer it is, right? And let me skip ahead for a little bit to tell you why is this important. So 1990, for 1 gigabyte of RAM, it cost $100,000. Hard to believe, right? 1995, Java comes out, and the price of RAM was down to $30,000 per gigabyte. Java 3 came out 5 years later. We're down to $1,000 per gigabyte. 2001, Scala got started. 2002, this program called Nuts got started, and Hadoop was part of that project, right? So when Hadoop was started, right, the cost of RAM was like $1,000 per gigabyte. MapReduce paper came out in 2004, and that's what Hadoop uses. And so that paper really influenced what development of Hadoop. 2005, F# comes out. 2006, Hadoop was separated from Nuts. 2009, Spark was started. In 2010, the cost of a gigabyte of RAM was $12. So when Hadoop was started, RAM was really expensive, like $1,000 per gigabyte. And it was designed to run on commodity hardware, and so they assumed the RAM would be very expensive and you would have much of it. So what Hadoop does is it keeps all data on the disk, and when it needs it, it reads it. Now, oh wait, that's really slow, right? When Spark was started, we're talking about $12 per gigabyte, right? And so one of the differences between Spark and Hadoop is Spark, it is going to load as much data and memory as possible, right? And so Spark claims is like 10 to 100 times faster. The main reason is because Hadoop was designed to keep data on disk and read it when it needed and write it back out, read it back in, right? And we're like, oh, that's really slow. But given the hardware at the time, that made sense. That was a reasonable design decision. Spark was started later enough that memory was really cheap, and said, look, this trend is just going to keep on going down. And so we can visualize a time when you can have a terabyte of memory, and so we're just going to load everything in memory, and that makes it much, much faster, right? And so given a choice today, if you're going to, between Hadoop and Spark, just in terms of performance, you pick Spark, right? It's always bad when a college professor starts talking, because they like to talk a lot, right? So we'll see everyone on Tuesday. Have a good long weekend.